So we are a lot of researchers working on this topic. So myself with Midwig Juan, Francesco Posella, Luca Biffarale from University of Rome Tor Vergata, Massimo Ciancini from CNR, and Alberto Carrassi from University of Bologna. First thing I would like to say is that except Alberto, everybody else here in our co-author list is new, almost new to data assimilation. So our field is turbulence. So what I would be focusing on is application of existing data assimilation methods for a low dimensional turbulent system, which is very multi-time and multi-scale. All right. Yeah, so this presentation has only 4 parts. First, I would try to explain what are the shell models of turbulent cascade that uh, on which we are going to apply ensemble data assimilation methods. And before we apply ensemble data assimilation, I would discuss a bit about application of 4D war without any ensemble so that we can appreciate the benefits of using ensemble data assimilation. In ensemble data assimilation, we only use ensemble 4D var and ensemble Kalman filter, after which I will summarize the results. So let's look at this model in a bit more detail. These are the model equations where UN represents a shell um, which represents fluctuations at wave numbers of the power of 2. So if we look at this energy spectrum versus wave number, then we see that this has a turbulence kind of a spectrum where energy is injected at large scales via this forcing term. Then it passes to smaller scales by this energy cascade. So here we have the inertial range. And finally, the energy is dissipated by the viscous term at small scales. So there are model constants A, B, and C, which look very simple, but these simple constants are actually very carefully calibrated so that the scaling laws and scaling anomalies in the shell model match very closely with what are observed for turbulent flows, for three-dimensional turbulent flows. Now, the shell model, the good thing about it is that even though we are covering a large range of scales, the system dimension remains very small. It's still only 20 complex numbers. So 20 shells are representing a wide range of scales. Having said that, I should also point out that the dynamics in the time is not simplified. So the time steps required to solve this system is still very small. It's a very stiff problem. Uh, so the time scales, they are ranging from the order 10 to the power 0 all the way to 10 to the power minus 3. So we have 3 orders of magnitude covered in the time scales. Now to have some appreciation of what it means, let's look at these 2 shells, one at the beginning of the inertial range, shell number 4, and one at the end of the inertial range, shell number 14. So these two have a separation of time scale at 2 orders of magnitude. Now I'll just play a movie on their time evolution. So we see the lower graph, the shell number 14, it remains 0 most of the time, but then it has these bursts. So it is going through several bursts while shell number 4 is just evolving slowly. A very important thing to note here is that even though shell number 14 on average has much lower energy, 2 orders or 3 orders of magnitude lower energy than shell number 4, but these shells are still very important because whenever they have a burst, this burst is pretty much same order of magnitude as shell number 4, and that causes basically backscattering and affects all the shells even upstream. Now the question that we ask is, if we measure shells a few scales in the inertial range, how much can we predict? Can we predict the larger, almost Gaussian scales before the inertial range, and can we also predict the smaller intermittent scales after the smaller scales than the ones those are measured? So what we apply first is standard 4D VAR, which has two parts: a background term and an observation term. So we are just going to minimize this cost function. Now, because what we assume is that the observations are very accurate, so there's only very small error in the scales that we observe. For the background information, we do not have much given to us, because as soon as we go to the shells which are not measured, we have a scale separation, so we have almost no information about the shells that are not measured by the background as such. Now when we apply 4D VAR, now the first question comes is, how long should be the data assimilation window? So we tried 3 assimilation windows. So if these gray region are the shells that I measure, we are going to use a data assimilation window of 500, which is a smaller time scale than the ones measured, 2000, which is equal to the fastest measured time scale, and a longer time scale of 5000. Now what we see is that if the time data assimilation window is too small, then we are not doing well in estimating the other shells. So on this left hand side, I have the normalized mean square error on the vertical axis, and on the horizontal axis, I have the shell numbers. The dashed line 2 here indicates the statistical reconstruction. So if the prediction fails completely, if they are only basically statistically correct, then the error should be 2. When the error is higher than 2, it means that we are failing to even predict statistically the intermittent shells. The result I show here is the filter, which means it is at the end of the assimilation window. So what we see is that when we use a very small data assimilation window, then we are not able to estimate beyond what we already measure. If we have too long an assimilation window, which means 5000, we start to lose estimation on the faster shells. So this is the effect of the multi-scale, multi-time dynamics. It becomes highly sensitive to the length of data assimilation window. A too short assimilation window is not enough. A too long assimilation window leads to error in the fast shells. Now the question is, how do we make the assimilation window longer so that we can estimate the large scales without compromising the accuracy on the faster scales? So there are two options. One is to use multi-time 4D VAR. So here we will have to play around with this second term, where we use observations on different time scales to estimate shells at different time scales, or turbulent fluctuations at different time scales. But we go for the second option, where we are going to use ensemble method so that we can get the background information using the ensemble spread, and then we can propagate that background information from one shell to other shell. So let me explain you what it means is that we are going to perform 4D VAR in sequence. So we perform 4D VAR in one assimilation window from 0 to TSM. At the end of this assimilation window, we are going to calculate the background information using the ensemble members. This background information would be fed at the sequence number 2, where we again perform the assimilation in the same window length, and so on and so forth we go on. Now we are going to ask a few questions about how many ensemble members do we need, what should be the length of the assimilation window, so this guy TSM, and how much do we need to measure to basically be able to have a good estimation of turbulent fluctuations. So let's look at the first question first, number of the ensemble members. So if we measure shell number 4 to 8, and the total assimilation, the total simulation time that we have is equal to T assimilation multiplied by N sequence, so in many sequences, and we run this simulation for 20 times eddy turnover time of the first shell. So we run the simulation for a very long time. We take out the transient out, and then we run the average over the rest of the time to calculate the mean square errors. We can already see from here that the measured shell is very well estimated. The lower shell is also very well estimated, but the faster time scales, so shell number 12 here, has some issues that we will see very soon. So this simulation runs with 40 ensemble members, and here I show the normalized mean square error for ensemble members 40 and ensemble members 60. So let me go through these plots, what they mean. So on the vertical axis, again, I have the normalized mean square error. On the horizontal axis, I have the shell numbers. So the left plot is the smooth solution. So at the beginning of the assimilation windows, the right hand plot is the filtered solution, which means at the end of the assimilation window. The top plots, they are calculated where the error is calculated and then the ensemble averaging is done. At the bottom, the ensemble averaging is done first and then the errors are calculated. So what we see here is that the number of ensemble members in this case is not making a big change. It increases the spread a bit, but does not make any significant influence on the results. Important thing to note here is these shells. So if we look at the smooth solution, it's accurate at the shells immediately after what are measured than the filtered solution, and that is expected because the correction is done for the smooth solution. But if we look at the higher shells here, then we see that the filtered solution is much better, and that's because these faster scales are decorrelated from the ones that we measure. So the governing equations, they are better at bringing these faster scales to the real solution, to the ground truth, than the 4D-VAR is. And very interestingly, what we see is that when we are performing this 4D-VAR in ensemble, we can actually estimate all the slower time scales very well because we are using very long information now. We are able to use very long information without having to increase the assimilation window of each 4D-VAR. Now let's look at when we measure shell number 6 to 8. So when we have basically less information, what happens is that in this case, we see the benefit of using more shells, more ensemble members. So with ensemble members equal to 40, we get destabilized solutions. So we have errors in the estimation. While when we have ensemble member equal to 160, then that helps us to stabilize and get better estimations. So here we can see with the time evolution of the shell number 2, 7, and 12. So on the horizontal axis, I have the time or the sequence number. And on the vertical axis, I have these shells. Here, shell number 2. The black lines are the ground truth. And the spread is the basically spread of ensemble members. So when we use 40 ensemble members, we actually are able to predict these large time scale shells, but the code is not stable, which means that there may be some error at some point, and then we are not able to come back to the ground truth. But when we use more number of shells, so 160 shells, then we find that the spread is larger, the transient time is also much longer, but the code is much stabler. So we have higher chance of staying close to the correct solution, to the ground truth.
Few more minutes, Vikrant.
Yeah, okay, thank you. I was talking about that. Now this is again how long do we use the window? So again, what we find is that if we use a very short window, we have unstable solutions where we are not able to basically propagate the information correctly. But if the window is too long, for example 2000 here, then also it's not optimal because we have again get error in the fast time scales. So still even in the ensemble 4D var, it remains very sensitive to the data assimilation window length for each of the sequence. Next is how much do we measure? So what we find is that if we measure some continuous scales, then we are able to propagate information downstream and upstream. But if we measure isolated scales, for example, this blue curve, then we are not able to estimate very well any other scale other than what we measure. Lastly, we have a comparison between ensemble Kalman filter and ensemble 4D var. So ensemble Kalman filter, we do not find any stable solution if we use members less than 500. So we have to use a very large number of ensemble members to stabilize the ensemble Kalman filter. But once ensemble Kalman filter is stabilized, it gives a bit better results than ensemble 4D var without having to play around with data assimilation window length and regularizations for calculating the Hessians. This is all. This is the summary. So what we find is that flow-dependent background information is quite important to assimilate multi-scale systems, and we find ensemble members are very good for that. Higher number of ensemble members lead to longer transient but stabler codes. The 4D var and ensemble 4D var are very sensitive to the length of data assimilation window. And lastly, we need to measure continuous scales so that the information can be propagated towards the faster and the slower time scales. If we only measure isolated scales, then we do not propagate information. The bad part is that at the moment we are using too many ensemble members. So maybe we need to reduce the ensemble members by using tricks like localization, for which I think the next talk is on. And the other thing is that I did not go much in the details, but we are not able to really estimate the intermittent scales very well. So if we go in the zoom in this figure, what we see is that the ensemble spread around the bursts is quite high. And I think that is where maybe the previous talks on stochastic particle filter maybe could be helpful. With that, I am done and open the floor to questions. Thank you.
Thank you, Vikrant, for a very clear talk on the impact of variational methods and ensemble methods for a multi-scale system like the one you are investigating. There are quite a few questions in the YoPad, and we have a limited time, so I'll start with the first one and we'll see how much we can cover. Peter Yan is asking, have you tried using solving 40 var on windows with increasing length?
Yes, so this is what the results is right here. So you mean that if I keep increasing the length beyond 2000, what happens is that, let me go a couple of slides back here. So when I'm using the length 2000, then we already have quite high error in the fast scales. If I go for further longer, window, then this error would be even higher, and at one point it will propagate upstream and destabilize all the estimated shells.
Peter Jan is currently writing a clarification of the question, so I suggest to take a look at the YOPAT after, and maybe you can have a discussion about it. I have a question myself, but I'll pass it for you to answer to myself in the YOPAT at the expense of other speakers. So Prashant is asking, in your 40-var experiment setup, background error and observation error terms are dependent on same parameters with different scaling. Why?
So I didn't quite get the question. So this is the background term, and this is the observation term. In the background, we have all the scales here, while in the observation, we only have the measured scales. So VK is the measured scale, right? The measurements at time K, and H is the observation operator. So I give the full U here, but when we pass it to the measurement operator, then we only get the scales that are measured. So the observation only contains the information about the measured scales, while the background contains information about all the scales. Now, because the scale separation is very high, based on only the observations, or let's say the correlation between the shells, we basically have very little correlation as soon as the shells are separated by 2. So we have very little background information based on the observations alone or based on the static information alone.
Thank you for this clarification, Vikrant. And there are 2 more questions in the YOPAT. Feel free to elaborate on all of them for the record. And otherwise, thank you again so much for your clear talk.